There we go. I don't know why the quality is so much worse on the projector when it's via Zoom. Mystery. 2.4, theorems on differentiation and higher order derivatives. Double title. We're just gonna kind of walk through different kinds of functions and see like if we can say anything intelligent about their derivatives. And every once in a while use our formal definition of the derivative in order to support what we're saying. But the first couple are kind of just going to be logic or just like common sense, I would say. So starting with the constant function. First, consider the constant function. F of x equal to c with c some constant. Let's just graph this thing. And let's say c is up here. Constant function for any c has a graph that looks like a horizontal line. And if we recall that the derivative is a way to measure change, or more specifically, the slope of the tangent line to a curve, how is the constant function changing? Not at all. It's literally called constant. It does not change. And if we try to picture, a tangent line to this curve, it's basically just a horizontal line. And so from that intuition as well, what's the slope of a horizontal line? Do we agree that 0 is probably a good way to say no change as well? So that's our first theorem here, is just noticing that at any point on the constant graph, slope of tangent is 0 because there's no change, it's constant. And indeed, our very first theorem on differentiation tells us so. Which is 2.4.1, the constant rule of differentiation. If c is a constant and f of x is equal to c for all x, then the derivative of f of x is equal to 0. There is no change everywhere. It's just the same. 0, 0, 0, 0, 0. You know what you're getting with constant. No excitement, no changes, no surprises. There's never any change. It should be kind of comforting in life, to find your constants. Pretty okay with that? Be on board with that? Okay. Because now we're going to look at the identity, which is a similar kind of argument. And again, we could formally show this with the definition of the derivative, but I think that's a little overkill. We'll just use our brains and our eyeballs. But now consider the identity function. F of x equals x. We'll again consider this graphically at first. Our identity function looks something like so. How's the identity function changing? Sophie.
By like 1, so like up 1 over 1.
Yeah, the slope of that line is 1. That's literally the definition of a line, is it has a constant rate of change. And so with the identity, that rate of change is just 1. And we're kind of going to jump ahead here and claim some stuff that we won't actually prove until a little bit later. But can we maybe see how this could extend to any linear function? What do we think the derivative of any linear function is going to be? So do all lines have a slope of 1? How do we know how a linear relationship is changing? What piece of information gives us that? Nathan? The slope of that linear function. We maybe get on board with the fact that for any linear function, its derivative is exactly its slope. That's what lines are. They're just like these perfect, beautiful, never changing, but constantly changing relationships. Which is why we freak out so much about them in algebra 2. It's like they're just so easy to work with. We know exactly what's going to happen no matter what and how it's changing. And so more generally, let's actually, before we leave here, be okay. At any point, finish the identity first. Our tangent has a slope of 1. i.e., if f of x is equal to x, and f prime of x is equal to 1. I don't think your book actually does as a formal definition, but it's kind of important. So sort of more generally here, any linear function will have a derivative exactly equal to its slope. Which introduces a very, 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 very important idea. Not just about linear functions, but about functions in general. But I'm going to use this basic linear idea to illustrate And this idea is that two different functions can have the exact same derivative. Say that again. Two different functions can have the exact same derivative. What you talking about, Mr. Smith? Talking about this, that a consequence of what I just wrote. Let's read what I wrote. More generally, any linear function will have a derivative exactly equal to its slope. Are there different linear functions that have the same slope? Yeah. For example, let's let f of x equal 2x plus 1 and g of x equal 2x minus 1. Graph these out. Here's f. It's got a y-intercept at 1, slope of 2. Something like that. Here's g. It's got a y-intercept at -1. Also a slope of 2. I'm already on the sort of retired this year for the app band. Last year during pandemic time, so professional audio and audio settings right now. My Prius died, and rather than replace the Prius, I bought an e-bike because at that time Smith was working from home. I really need 2 cars. And it was easy enough for me to ride the e-bike up Stone Hill and just get to work that way. It was about 2 miles from there. And that worked well for that time. But then we had a kid, and even for the first few months with the kid, it was okay. But then summer rolled around, and Mrs. Smith went back to the office, and she had to drive to the office. And I figured, I'm watching Big Nora now. Yeah, I could probably scooter around on the e-bike, but if there was like some emergency situation, I'd probably want a car. So we went full dad mode. We got the minivan on the Odyssey. I know people like to hate on the minivan, but let me tell you, that thing is functional. Little known fact about minivans that might interest you. Have I told you about the minivan little nugget and the landfill? Oh, yeah, never true. So let's say you got some big house project and you're doing some demolition and you end up with a big pile of crap in the garage. You can't just put that in your residential trash can. I mean, I guess you could be like really stingy and just do like a little load each week for like the CBRE guys, but that'd be kind of lame. And if you were married to my wife, she'd be like, "You're not doing that. Let's get rid of this trash." And so what you could do is call a friend who has a truck, like, "Hey, John, I got a bunch of stuff. Let's go to the landfill." Like, "Yeah, sure. I'm gonna get the truck. People call me all the time." And you throw all the stuff in the back of the truck, and then you get to the Prima Desheka landfill, also known as San Juan Hills neighbor. Yeah, so like a dump there. Where you're happy you're not a stallion. Go Dolphins. Sure, they have nicer things than us, and all their buildings are super clean, but they're literally about there. And when you get to the dump, they'll look at the pickup truck and say, "Give me $20 to get into the dump." And you'll hand them $20, and then you go deposit all the crap. Let's rewind a little bit. If you had thought ahead a little bit and not been, intoxicated by the sexiness of a pickup truck and thought, "You know what, I'm gonna go practical. I'm gonna minivan." You show up the minivan with that same stuff in the back of your minivan, because let me tell you, you pull the middle seats out of that Odyssey, you pop down the back, it's got as much, if not more, storage capacity than a pickup truck. You know what happens when you show up to Kunjasheka landfill? They charge you $5 because the passenger vehicle, not a pickup truck. What's the savings there? 15 American dollars. So I'm just saying, don't sleep on the minivan. They're pretty awesome. Why did I start talking about that? Oh, yeah, because Kelly Hart called up and was like, hey, is your e-bike parked outside? I said, no. I'm all about the minivan like that. So. Anyway, what were we talking about? Linear functions. And here I said I wasn't going to divulge anything about my personal life today. You guys just dragged it out of me. You're so needy. So we've got f of x in green. Got a slope of 2. G of x is about to hit the streets in purple, up 2 over 1. That's a true story, by the way. $5 to get into the dump with a passenger vehicle, $20 for pickup truck. Just saying. And then we draw the line. And that's not the best work I've ever done. Those lines should be parallel. They don't exactly look parallel. I don't want that. Do we agree that those are different lines? Represented by different functions. But can we also agree that they are changing in exactly the same way? Yeah, their rate of change, their slope is identical. So both of these things, the derivative of x, sorry, the derivative of f is 2. What's the derivative of g? Also 2. Different functions, the same derivative. And so an idea that will become important later in life, 2 different functions can and often do have the same derivative. Simply means they change in the same way. Okay. So I'm going to do my best to always kind of like bring it back to this idea of change. Because we're going to start to get like a little nitty gritty with some of these details. The derivative is measuring change, that instantaneous change of a moment. So we're going to look at kind of the big reveal today, and then probably circle back and use that big reveal to support what we said here a little more rigorously. And then see where we're at and go from there. So here's the big reveal. I'll call this the big reveal because I just said it. Big reveal of easy derivation. Derivation, process of finding the derivative. And the big reveal is the power rule. The what? The power rule says if n is a positive integer, and if f of x is equal to the power function x raised to the nth power, then the derivative of f is equal to n times x raised to the n minus first power. Now, for the moment, we're going to restrict this to positive exponents, but by the end of the day, we will have dropped that restriction. And so just to kind of do a quick illustration of how beautiful this is. Quick illustration before we prove this, because we will prove this, because this is pretty important. Remember, f of x equal to x minus 2 to the negative 2. And I'm breaking all kinds of rules here because this is not a positive integer, but it's still going to work. And technically, there's a situation we would have to address that this is a composite function in here. But just bear with me, just to give you an illustration of how easy this is. If we want the derivative here, this is a power function being raised to the negative 2. F prime of x. Check out this black magic. Take this exponent, drop it down. Negative 2 times x minus 2. And then take this exponent and subtract 1. X minus 2 to the negative third. Did I say 4 seconds? That might have been 7 seconds. I don't know. That's the derivative. No need to do the crazy limit of f plus x plus delta x minus f of x over delta x as x approaches 0. It would have taken us probably 7 or 8 minutes to get here. Just drop that exponent down, subtract 1 from the exponent. That's it. You dirty dog, Mr. Smith. Yep. So this is going to revolutionize your lives, especially in terms of polynomials. Our fetish with polynomials will start to kind of emerge today, that they're just so easy to work with when we're talking about derivatives. You just power rule, power rule, power rule, power rule. Easy, easy, easy. Okay, but before we get too carried away, let's see if we can use that terrible definition of the derivative that we're trying to put in our rear view mirror to prove that this is actually true. Because it's one thing to like say that it works and maybe even see that it works for a couple of specific situations, but proof carries a slightly higher level of rigor there, that it's going to work every time, or rather we want to show that it's going to work every time. So let's see if we can do that. Proof. Now, before we get to nose deep in the proof, we're going to do a quick reminder on the binomial theorem, which I kind of hinted at last week with Pascal's triangle. Did we talk about Pascal's triangle? Yeah. And I told you that if you put a gun to my head, asked me to recite the binomial theorem, I probably couldn't do it. It's true. But here's the binomial theorem. In general, the binomial theorem allows us to do binomial expansion. Binomial what? What does that mean? It means if we have a plus b raised to the nth, and like when that's a 2, no big deal, we just FOIL or do whatever. Even when it's a cube, it's not that traumatic. But like the higher these things get, if we're just gonna brute force multiply over and over, that becomes terrible. And so it's nice to have a formula that tells us exactly how they're going to expand. And so the formula says this will be equal to a to the n plus n choose 1 times a to the n minus 1 times b plus n choose 2, a to the n minus 2 times b squared. That's what's happening with our exponents. The n's are decrementing, I don't know if that's a word, decreasing by 1 each time. The exponent on the b is increasing by 1 each time. And so we'll do the magical ... The last two terms then. Let's not worry about the choose just yet. But the second to last term, we would expect to have a to the first power and b to the, what do we think? B was increasing 1 each time. Maybe let's answer it this way. The final term is going to be b to the n. So what's the exponent on the last, or second to last b going to be? B to the n minus 1. Which also helps inform this last choose. We've got n's the whole way. The bottom seems to line up with the exponent on 2, or on b. Here it was 1, here it was 2. I'm guessing here it's going to be n minus 1. I know we're freaking out about this symbol here. We'll visit that in a minute. But this is the binomial theorem. Why do we need to know the binomial theorem? Because watch what happens when we try to use the formal definition of the derivative. Let f of x equal x to the n. You don't know what n is, you don't know what n is, it's fine. Could be anything. Well, it has to be a positive integer at this point in our lives. Then definition A of the derivative says that the derivative of f can be found by taking the limit of f of x plus delta x minus f of x divided by delta x as delta x approaches 0. Now, what does that mean for our function? For our function, it means taking the limit as delta x approaches 0 of f of x plus delta x, with our definition of f, means x plus delta x to the nth power. Oh, that's why we need the binomial theorem. Minus f of x, which is just x sub n, all divided by delta x. This right here binomial theorem. Because if we just try to plug and chug here, put a 0 in there, this turns into x to the n minus x to the n is 0, divided by 0, indeterminate. We're going to have to expand this out via the binomial theorem and hope that a bunch of stuff cancels out. Oh. That doesn't seem very fun, Mr. Smith. Yeah, well, nobody said it would be fun. We're going to do it anyway. It's actually kind of fun. There's kind of a satisfying logic here, or maybe just for me. I don't know about you. So we're going to expand this and see what happens. This turns into the limit as delta x approaches 0. We're going to need like 2 lines up top. I'm going to do some big brackets. We're going to do the binomial theorem to expand x plus delta x raised to the nth power, where x will be a, delta x will be b. And so we're just going to basically plug in to this guy here. So with x as a, the first term in this expansion is x to the nth power, a to the n, x to the n, a to the n, x to the n, plus, and choose one, x to the n minus 1, b is delta x, times delta x to the first power. Plus, and choose 2, x to the n minus 2, delta x squared. Magical dots, plus, and choose n minus 1. We're going to have a to the first. We're going to have x times b to the n minus 1, delta x to the n minus 1, plus b to the n, delta x to the n, and then like the part we really can't forget here is that this is all subtracted by x sub n. And all of this is still part of a quotient whose denominator is delta x. We're going to do this in 2 steps, that's fine. What's the first thing we notice is going to cancel out? X to the n, heck yeah. Later x to the n. So what we're left with is the limit as delta x approaches 0. Yeah, let's do 2. And choose 1. X to the n minus 1 times delta x, plus, and choose 2. X to the n minus 2 times delta x squared, plus dot, and choose n minus 1 times x times delta x to the n minus 1, plus delta x raised to the nth power, all divided by delta x. Check it out. Check it out. Every single term in your numerator has what? A delta x, which means we can divide delta x from the denominator into every single one of these. Let's go ahead and do that. Later, delta x. Later, one of these delta x's. Later, one of these delta x's. Later, one of these delta x's. Later, this troublesome delta x in the denominator. Oh, we're getting somewhere. We're getting somewhere. Got rid of the 0 in the denominator. We're getting close. We're getting close. The limit as delta x approaches 0 now looks like this. Got rid of the denominator. This is now just n choose 1 times x to the n minus 1. No longer has a delta x in there. Plus n choose 2 times x to the n minus 2 times delta x, there's still one there, plus dot, plus n choose n minus 1 times x times delta x raised to the n minus 2 plus delta x raised to the n minus 1. Riddle me this. If we let delta x go to 0, what's going to happen to this term? What's going to happen to this term? What's going to happen to this term? What's going to happen to all the terms hiding in the magical ellipses? They all have at least one delta x. So as delta x goes to 0, every term but the first goes to 0. So as delta x goes to 0, every term but first also goes to 0. Which tells us that the derivative here, f prime of x, is equal to this first term. All these are going to 0. And choose 1, x to the n minus 1. And then we're like kind of looks what we wanted. Got the x to the n minus 1. We got to go in the Wayback Machine and remember, what the heck does this mean? I mean, kind of just casually means how many ways can you order n things one time? That should be, well, it's n times. But let's be a little more rigorous than that. This guy here, n minus or n choose k in general is going to be n factorial. Oh, you didn't think we were going to do factorial today, did you? A little treat over k factorial times n minus k factorial. I'm sorry, this is not ordering n things k times, it's choosing k things out of n. But I kept saying n choose 2, n choose n minus 1. If we just wanted the orders, or if we wanted the orders, we wouldn't have this. Nk, what are you talking about, Smith? Let's adapt this to what we're looking at. We're looking at n choose 1. So Rk is 1. Means we want n factorial over k factorial, which is like 1, times n minus 1 factorial. Still not sure I see this, Smithy. Just wait. N factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4 all the way down, which is also n times n minus 1 factorial. Oh, okay, yeah, that checks out. What's 1 factorial? 1. We're just dividing by n minus 1 factorial. And so n choose 1 is exactly n. And so this almost close to what we want thing is actually exactly what we want. The derivative here is n times x to the n minus first, which is what we set out to verify. Thank you, binomial theorem. I didn't know how much I missed you until I knew. And the power rule is now going to just revolutionize our lives. Yeah, we're going to push through to at least one example to see just how revolutionary this is going to be. and then we'll take a smoke break, and then we'll press on. Onward and upwards. Yeah, we're good. So before we see the true majesty of the power rule, there are two kind of auxiliary. Ancillary mean like kind of side. Where's my English nerds? What's an ancillary method? I think ancillary and auxiliary are pretty similar. Really, you guys are gonna pass the AP Lit test? You don't know the difference between auxiliary and ancillary? You disgust me. Am I just making up a word? No, I'm. At least I know how to annotate. All right. That's fine. Ancillary. That's how you say it. Ancillary. Providing necessary support to the primary activities or operation of an organization, institution, industry, or system. Yeah, ancillary. These are like ancillary things to the main thing. I think that's even more apropos than auxiliary. These are not auxiliary theorems, they're ancillary theorems. Anyway, Schmidt, stick to math. You're not too good at English. Yeah, I know. Okay, 2.4.4. So some, and just so you guys know that it's a real word, ancillary, that's ancillary theorems. First, sum. Starting with the sum rule. 2.4.4, the sum rule. Which just says we can add the derivatives of functions. If f and g, let's enunciate, f and g are functions, and h is defined by f plus g, h of x is f of x plus g of x, then supposing that both f prime of x and g prime of x exist, then h prime of x is just the sum of those two derivatives, f prime of x plus g prime of x. And then ancillary theorem number 2, I don't know, we're going backwards here, but this is 2.4.3, the constant multiple rule. If f is a function, c is a constant, and g is g of x equal to c times f of x, then if the derivative of f exists, g prime of x is simply c times that derivative. Which is one way to support the claim that the derivative of any linear function is its slope, because any linear function can be written as a constant times the identity. And we claim that the identity, I don't know why this is so, there we go. That the identity function had a derivative of 1. So any linear function is really just a constant multiple times that identity function. Okay, so now that the ancillary stuff is out of the way, let's tackle our first polynomial. I'll take a quick break. This is example 1. Find f prime of x, the derivative of f, if f is 7x to the 4th minus 2x cubed plus 8x plus 5. First, pause for just a moment and just do a little mental exercise here and picture the sheer brutality of having to compute this derivative with the definition of the derivative. Yes. The constant multiple rule. And G is, yeah, sorry, it's an ampersand.
In the previous one, the sum rule, is it like if f prime of x and g prime of x exists, then that
Did I not put exist? Yeah, okay. Forgot that important word. Yes. They need to exist. Otherwise, as we saw in example 14, can't add two things if one of them doesn't exist. I mean, try, but probably not going to work very well. So back to the mental exercise of just picturing the sheer brutality of having to put this into the definition of the derivative and compute that limit. You would have to expand a 4th power binomial because you would plug in x plus delta x to this, and you have to expand 7 times delta times x plus delta x to the 4th, and then you have to expand x plus delta x to the 3rd. Then you have to do the distribution on 8 times x plus delta x, and then like hope a bunch of stuff cancels, and then start crossing stuff out. And can we appreciate it would take a lot of effort, and you have to be really careful, kind of stuff. Well, now armed with the power rule, the sum rule, and the constant multiplication rule, let's just breeze through this. Applying the sum, and we could have put difference rule as well. We can break this into a sum of 4 different derivatives. The derivative with respect to x of 7x to the 4th plus the derivative with respect to x of negative 2x cubed plus the derivative with respect to x of 8x plus the derivative with respect to x of 5. And even this step right here is overkill. And eventually, almost immediately, we won't be doing this. But I just, for this first example, want to show that this is what's happening, even though the mechanics are basically going to just blow past this step. The first guy here, the power rule says drop down that 4. And then the constant multiple rule says we can multiply. Well, I guess we should do it that way. Yeah, we'll be a little more thorough than even we need to be, just to one time do it legit. The constant multiple rule then says we can pull out these constants. 7 times the derivative with respect to x of x to the 4th plus negative 2 times the derivative with respect to x of x cubed plus 8 times the derivative with respect to x of x plus, that's just still the derivative of 5. I'm showing what rules are actually being applied when we do this. But again, in practice, you're just gonna be able to look at 7x to the 4th and say that the derivative is 28x cubed, because it'll just become that automatic. Now we're gonna apply the power rule, because technically the power rule is only on x to the n. It's not on a times x to the n, even though in practice it kind of turns out to be. So now actually doing the derivatives. We'll have 7 times the derivative of x to the 4th. Drop down that 4. Subtract 1 from the exponent. X to the 4th has a derivative of 4x cubed. Over here, same thing. Drop down that 3. Subtract 1 from our exponent. 3x squared. The derivative of x is 1. And the derivative of 5 by the constant rule is 0. And so our derivative is 28x cubed minus 6x squared plus 8. But very quickly, as in like probably on your homework tonight, if you see a polynomial, you should be able to do this in your head. Because basically all we did was we multiplied the 4 by the 7 to get 28, subtracted 1 from the exponent. We multiplied the 3 by -2 to get -6. We subtracted 1 from the exponent. We multiplied 8 times 1. That was our exponent. Subtracted 1 from the exponent. X to the 0. That's just 1. And then the derivative of 5 is 0. I showed these 3 intermediate steps to show you, yeah, there is kind of some mechanics going on here. But in practice, from here to here should become very, 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 very easy. Do you agree that that's pretty easy? We all can multiply, right? Yeah. Most of us. Can we all subtract? Most of us. Then you can do derivatives of polynomials. And that's why polynomials are just like the bee's knees, or part of the reason. Because if we want to know how they're changing, it's so fast to get the function that tells us how that function is changing. And that can be a very powerful thing to know. Questions? Thoughts? Feelings? Everybody's feelings in here. I got 9:06, exactly 9:11. We will resume. Ancillary. I'm going to pause the recording. Somebody's got to remind me to unpause the recording. So the power rule is awesome. And the sum rule is cool. But like we might have situations where we're multiplying stuff together. And remember when we were doing limits, and it was like really nice when we discovered that the limit of the product of 2 functions was the product of their limits. We're like, oh, cool. You just like do it whatever order you want, and you get the same limit. So we're going to ask that same question and have that same hope. So this is going to be an illustration to show the need for something. This is illustration 5, but whatever. Question. Is the derivative with respect to x of f of x times g of x, does this behave like our limits, where this is going to be equal to the derivative with respect to x of f of x times the derivative with respect to x of g of x? Pretty nice if it was. But you can probably tell from the way I'm posing the question that it's probably not going to be. But, you know, maybe I just ruined your surprise. Let's consider a function called h. He's a nice fella. He looks like this. let h of x be like, I don't know, 2x cubed minus 4x squared times 3x to the fifth plus x squared. Now, real talk, if you're ever walking down the street and you bump into a function that looks like h, and I'm telling you, you need to find the derivative of h, here's what you should do. You should multiply this out with some double distribution. So 2x cubed times 3x to the fifth is like 6x to the eighth. 2x cubed times x squared is like 2x to the fifth. Negative 4x squared times 3x to the fifth is like negative 12x to the seventh. And negative 4x squared times positive x squared is like negative 4x to the fourth. What about FOIL? I don't like FOIL. Just double distribute. Distribute the first thing, distribute the second thing. Anyway, that's my pet peeve. So then the derivative, so now we've got a nice polynomial function. And like I said, polynomial functions are the bee's knees when it comes to differentiation because it's so straightforward. If we want h prime of x, we just power rule this thing into oblivion. Drop down the 8. What's 8 times 6? What's 8 times 6? 48. What's 8 minus 1? This is 48 x to the seventh for the first term. The second term, what's 5 times 2? It becomes 10x to the fourth, subtracting 1 from the 5. Negative 12 times 4. A little trickier, but pretty sure that's negative 84. Times x to the sixth. We need to start getting better at this. And then negative 4 times 4 times x to the third. There we go. That's how easy it is. Okay, 12 seconds flat. So that's how you should do the derivative here. Turn it into a true polynomial and then do power rule because it's easy. What we're trying to think about is the possibility that if we were to have taken the derivative of this guy, maybe calling it like f, and then taking the derivative of this guy, maybe call it g, and then multiply them together, do we get to the same spot as we do here? Because this feels correct. Like we just multiplied, which is fine, and then we applied these power rules. We're pretty confident that this is the correct derivative. So let's see what happens then if we allow f of x to be this first parentheses. 2x cubed minus 4x squared. And then let g of x be the second part. 3x to the fifth plus x squared. And the reason we're saying that is because now, h of x would be thought of as f of x times g of x. F of x, g of x. Well, let's look at these derivatives separately. F prime of x would be 6x squared minus 8x. And g prime of x is going to be 15x to the fourth plus 2x. Power rule, power rule. So then the product of the derivative of f and the derivative of g would be 6x squared minus 8x times 15x to the fourth plus 2x. Do some double distribution here. We're going to get like 90, maybe? 90x to the sixth plus 12x cubed minus, somebody help me. Thank you. Minus 120x to the fifth minus 16x squared. Is this thing the same as this thing? It doesn't look like it. So unfortunately, we don't get the nice kind of simple version for products here. So what this means is for h of x equal to the product of two functions, in general, it will not be true that the derivative of h is the product of the derivatives. We're going to do a big slash. That kind of sucks. Nice. Because less so with polynomials, because polynomials will always have this escape route where we can just go from a product to a sum. But we will very quickly be dealing with products of functions that we're going to need to figure out the derivatives separately and then worry about the product. And so we really want there to be a product rule. So is there one? The answer is yes. Just not quite what we expect. I don't think we're going to prove this. No, we're just going to give it to you and show you that it works. Taking the easy way out. Here's the product rule. And this is definitely something you need to memorize. 100%. 100% need to memorize this. This one's pretty easy to memorize, but you still need to do it. This is 2.4.6. The product rule. If f and g, sorry, enunciate, if f and g, certainly can't. If f and g, that's an ampersand, not a d, f and g are functions, and h, another ampersand, is the function defined by h of x is the product of f times g. H of x is equal to f of x times g of x. Well then, supposing that both f prime of x and g prime of x are in existence, and if, sorry, there should be an if in there, if those two things exist, the derivative of h will be f of x times the derivative of g of x plus the derivative of f times g. What? Or kind of the way that I think will stick in your brain a little better, but maybe not. Maybe you're just love function notation, which is fine. Kind of weird, but fine. Here's how I usually put it in my own brain. If you've got a function h that is the product of some first function times some second function, here's what the product rule says. The derivative of h is going to be the first function, which we'll do capital F, times the derivative of the second function, plus the derivative of the first function times the second function. And the beauty here is because of the associative quality, is that the right one? Associative lets you switch things around, or that's parentheses. The communicative, thank you. Because of the communicative quality of both multiplication and addition, we don't need to get our panties in a bunch about the order here. As long as you're taking the derivative of one times the other, and then adding it to the derivative of the other one times the other one, you're going to be good. So we write it as the first times the derivative of the second plus the derivative of the first times the second. But it doesn't matter what order you do it in because it's adding and multiplying. Okay. But it's good to get into some sort of pattern. So let's confirm that this actually works. We're not going to prove this, even though we probably should, but you know, time, whatever. Illustration 6. I don't think we've done 5 illustrations, but this is what it says in my notes. I'm a slave to my notes. Illustration 6. We're going to revisit the function we just looked at, which was h of x. And we had 2x cubed minus 4x squared times 3x to the 5th plus x squared. If we allow this guy to be our first function, this guy to be our second function, here's what the product rule says the derivative of h of x should be. It should be the first thing, 2x cubed minus 4x squared. That's the first thing, times the derivative of the second thing, derivative with respect to x of 3x to the 5th plus x squared, plus the derivative of the first thing, f prime, times the second thing, 3x to the 5th plus x squared. First thing times the derivative of the second thing plus the derivative of the first thing times the second thing. All right, let's see if this actually gets us to where we're expecting, which if you recall where we're expecting to get to is 48x to the 7th plus 10x to the 4th minus 84x to the 6th minus 16x cubed. We're going to leave this alone for now, the first thing. 2x cubed minus 4x squared. The derivative of 3x to the 5th plus x squared, thanks to the power rule, is 15x to the 4th plus 2x. The derivative of 2x cubed minus 4x squared is 6x squared minus 8x times the second thing, which is 3x to the 5th plus x squared. Now we're going to have to do some double distribution. 2x cubed times 15x to the 4th is like 30x to the 7th. 2x cubed times 2x is like 4x to the 4th plus negative 4x squared times 15x to the 4th is like negative 60x to the 6th. And negative 4x squared times positive 2x is like a negative 8x cubed. 6x times 3x to the 5th is like 30, no, that's not true, 18x to the 7th. 6x squared times x squared is like 6x to the fourth. Negative 8x times 3x to the fifth is negative 24x to the sixth. And negative 8x times positive x squared is negative 8x cubed. Let's hope there's some like terms in here. My x to the seventh terms are 30x to the seventh, 18x to the seventh. Pretty sure that makes 48x to the seventh. My x to the fourth terms are 4x to the fourth and 6x to the fourth. That's like 10x to the fourth. X to the sixth is look like negative 60x to the sixth, negative 24x to the sixth, like negative 84x to the sixth, and then I've got two negative 8x cubeds. I'm really hoping we didn't make any mistakes along the way. Negative 16x cubed. Let's see, moment of truth, 48x to the seventh, check. 10x to the fourth, check. Negative 84x to the sixth, check. Negative 16x cubed, check. It worked. Now, let me be abundantly clear here. Would you prefer to do this or this? What was more of a pain in our butt? To do this and use the product rule, or to multiply first and then just do the power rule? Second one was harder, right? So this is a very contrived example. With polynomials, it's usually going to be worse off to use the product rule. Okay? Where the product rule really kind of takes flight is when we're multiplying two things that don't play nice. These things play nice. You can just multiply them out and you've got a polynomial. If, for example, though, we had like x cubed times the square root of x minus 7 or something, those things don't play so nice. And that's where the product rule is really going to be like, oh yeah, good stuff. Okay. Okay, we're going to blitz through the quotient rule and then look at our tests. Okay. Quotient rule, I'm just going to give it to you because it's a weird one. We're going to practice it in one example, and then we'll basically be out of here after we see the tests. So the quotient rule. Again, it's not going to be quite as nice as limits. 2.4.7, the quotient rule. And this is another one that you need to commit to memory. Will be a slightly trickier thing to do than the product rule because unfortunately subtraction is not commutative. Subtraction, that we're talking about quotients, just wait. If f and g are two functions and h is the function h of x is equal to f of x divided by g of x, where we're going to restrict g to not equaling 0. Balance up. Then, supposing that both the derivatives of f and g are things that exist, the derivative of h is defined as the following. G of x times the derivative of f of x minus f of x times the derivative of g of x all divided by g of x squared. Woof. Yeah, that one's a little bit hairier, especially because the order here is of crucial importance. Product rule, it didn't really matter. It's just like you can commute those things as long as you're taking the derivative of one times the other thing and then adding it to the derivative of the other thing times that thing, you're good. Here, we need to make sure that we're doing it in the correct order because subtraction, not commutative. So sort of the, I don't know, maybe more sticky for your brain way of seeing this that I usually keep in my brain is if we let h of x be a numerator divided by a denominator, got some numerator function, some denominator function. Because again, g's and f's and just, I don't know, get a little bit dicey. Then what the quotient rule says is that the derivative of h is going to be the denominator, d, times the derivative of the numerator, n prime, minus the numerator times the derivative of the denominator, divided by the denominator squared. Which to me is like a little more palatable, but yeah, that's just me. The thing to notice is the denominator stays in the same place, it just gets squared. Do you have attendance things for me?
Yeah, I think you're today.
Oh, this is a call slip.
Yeah.
Yes, he is.
Okay, good, thank you so much.
Mr. Duffield, we've got an update regarding your Chromebook. Has been repaired. Please bring the loaner Chromebook named barcode 171263 to the library and we'll exchange it for your repaired Chromebook. No, I know you wouldn't want to leave at this moment of high suspense, so I imagine you can do that at any time. Ah, shucks. Okay. Do we even? Yeah, we're gonna blitz through an example. So the denominator stays in the same spot, you square it, and then the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Whew. Let's see what this looks like in practice. You know what? No, we'll just table this. That's fine. Your homework. We'll do the example of the quotient rule and the rest of the lesson on Thursday. We're going to call this 2.4a. There will be another assignment associated with 2.4. So 2.4a is on page 141. Make sure that what I'm saying here isn't too egregiously aggressive. Aggressive, yeah. 4 and 5 with. Oh, yeah, for sure. Okay, you're gonna do numbers 4 and 5, but listen to the directions or you will not get full credit. For 4 and 5 only. First, find f of x using 2.1 definition. So that's the limit. Then confirm with 2.4 theorems. So those will take you a minute. Then I want you to do uh, 6 through 12, where you're just doing the theorems. You're gonna see that's gonna take you very little time. And then you're gonna do 20. Yeah. Yeah, 20 through 24. Those are going to be product rule. I'm not signing any quotient rule because we didn't do an example, but you will have some in 2.4b. Okay. Stop recording.